I want to just do a very quick visual for instantaneous velocity as the slope of the tangent line and how that comes about from taking the limit of the average velocity as a function of time. Should have a vector arrow over the top for that position. So the instantaneous velocity is the average velocity as you shrink the time interval. And we're also saying that becomes the slope of a tangent line. My favorite curve to do this with is x equals t squared. That's x on this axis and t on this axis. So it's the slope of the tangent line, but it's also the limit as delta t goes to 0. So let's go ahead and choose t equals 0 and x equals 0 at t equals 0 and x equals 0 as our example. If we pick a very large delta t, that delta t to start with, that has a delta x that looks like this. The average velocity, so the slope of that line would be the average velocity, would be delta x over delta t. That's true always. As I shrink the time interval, so the time interval was this big, if I make it this big, then the line looks like that. And if I make it even smaller, looks like that. I hope that you can see that as you shrink the time interval here, and you're only looking at this point, as the time interval shrinks, you get a closed slope that's closer and closer to 0. And indeed, separate picture, I've drawn so much all over that one. It's easy, might be easier to see if I had a full parabola for the t squared. This is still x equals t squared. I just drew the negative time values as well. You can see that if you imagine drawing a tangent line at that point, at the point t equals 0, x equals 0, the tangent line would indeed be a flat line with slope 0. So the slope of the tangent line is the same thing that we get by shrinking the time interval. And that's what that limit means, that we imagine shrinking the time interval, and that becomes the slope of the tangent line.